Hey, everybody. Welcome to today's episode, which is Frequency Explained. Today, we're going to go over frequency in hertz, hertz in lasers, applying hertz to your laser, and then we'll wrap things up. So, what are hertz? Well, hertz is the unit of frequency in the International System of Units. They're named after a German physicist, Heinrich Rudolf Hertz. Frequency, measured in hertz, refers to the number of cycles or wave oscillations that occur in 1 second. For instance, if a wave completes 1 cycle per second, it has a frequency of 1 hertz. To express larger frequencies more conveniently, we use prefixes such as kilo, mega, and giga, which are 1,000, 1 million, or 1 billion hertz for cycles per second, respectively. In pulsed lasers, frequency in hertz indicates how many pulses occur per second. For example, a laser pulsing once per second has a frequency of 1 hertz. It's common to see consumer-grade pulsed lasers operate between 1 kilohertz and 4,000 kilohertz or 4 megahertz, but many are much more limited. Frequency is an important factor in calculating a laser's average power. Power in watts is calculated by multiplying the pulse energy in joules by the frequency in hertz. So watts equals joules times hertz. For example, a laser with a max pulse energy of 1.25 millijoules and a frequency cutoff at 40 kilohertz outputs how much average power? Well, 1.25 millijoules expressed in joules is 0.00125, and 40 kilohertz expressed in hertz is 40,000. So 0.00125 times 40,000 is 50. We have a 50-watt laser. Frequency cutoff means that anything below that threshold will not produce the maximum average power that the laser is capable of. For example, the 50-watt laser from above would only produce an average power of 37.5 watts at 30 kilohertz. At frequencies above the cutoff, the average output power stays the same, but there is a drop in the max pulse energy as the kilohertz goes up. For example, that same 50-watt laser, when set to 210 kilohertz, produces how much pulse energy? Well, the answer is 0.000238 joules or 0.238 millijoules. The lower pulse energy explains why lasers do less ablation at higher kilohertz and do things like create oxide layers on metals or vaporize coatings without damaging the base material. In general, setting your source to the cutoff frequency and, if it allows, adjusting your pulse width to the longest duration is going to deliver the most energy and get the most work done in the sense of removing or cutting material. Using slightly higher kilohertz settings will help you smooth engraved areas and remove lines or other artifacts from the engraving. Using even higher frequencies will allow you to deliver higher levels of heat in the form of IR energy to the material without high pulse energies wanting to remove material. This is good for annealing metals and other uses like vaporizing coatings where underlying material removal isn't desired. In order to understand how to apply frequency and hertz in your laser, first you need to know your laser source. Alex did an outstanding series of videos on how to do just that, and I'd refer you to them. Once you have, then you can determine what is your cutoff frequency, what are the minimum and maximum frequencies, and can you manipulate your pulse duration. All of this information can be found in your laser source's owner's manual or on the spec sheet that most reputable laser system manufacturers provide with their machines. Here's an example of a spec sheet from a JPT laser. This is a YDF-LP series 50-watt LP laser. This has a maximum pulse energy of 1.25 millijoules, a pulse frequency range between 1 and 600 kilohertz, and a full power frequency range between 40 and 600 kilohertz. This means that this laser will produce 50 watts of optical power between 40 and 600 kilohertz. In contrast, here is a spec sheet from a Raycus laser of comparable wattage. This is the RFL P50QB. And you can see here it has a nominal average output power of 50 watts and a single pulse energy of 1 millijoule at 50 kilohertz. As you can see, along with the lower pulse energy, this also has a much more limited pulse repetition rate between 50 and 100 kilohertz. Some lasers will allow you to manipulate their pulse width, sometimes referred to as pulse duration. Pulse width is measured in nanoseconds or billionths of a second. Adjustability can range from 1 to as much as 500 nanoseconds. The duration of the pulse will affect the maximum pulse energy. Here's an example of another JPT laser, a YDFLP-E2 100 watt laser. This has an unlocked pulse width and, as you can see in the left-hand column, has 17 presets to which you can set the pulse duration. Each one has its own cutoff frequency, and each one has its own max pulse frequency. The reason for this is that shorter pulses have lower energy, therefore there need to be more of them in order to make up for the wattage. So in this instance, a 9 nanosecond pulse duration would require 960 kilohertz or 960,000 pulses per second in order to produce the 100 watts of power. As I understand it, all of the pulse width numbers in the left-hand column are preset into the firmware of the laser source, meaning if you were to input a number different from those in that column, the system will automatically default to one of the presets, and it seems to be the one that's closest. So if you were to put 67 in for the pulse width, it seems that the system would default to 60 and your kilohertz settings would change appropriately as well. As you can see by this chart and what little I've explained of it, pulse width and pulse frequency are very much intertwined. You can lower pulse energy by shortening the pulse width, or you can lower the pulse energy by increasing the frequency, or you can lower it even more by doing both. So it's a very complicated game of adjusting the duration of the pulse, which is an adjustment of the energy of the pulse, and adjusting the frequency of the pulses, which is, again, another way of adjusting the energy of the pulse. So good luck with that. So to wrap things up, today we learned what frequency is, how frequency works in pulsed lasers, how hertz affect laser average power, how to determine your laser's range, and how pulse width and kilohertz work together. I really hope that this helped answer any questions that you might have about kilohertz with fiber and other types of lasers. And if there's anything else that maybe I didn't address and you'd like to see, maybe leave a comment and let me know. Thanks a bunch. I really appreciate your time, and you guys have an